Whenever you want, Jarrod.
Thank you. And hola, Wasamigos. Thank you so much. And by the way, that should be obviously what we call ourselves, right? Like, that's so much better than a lot of other things I've heard. And Wasm is not a very easy word to string against other things. But thank you very much for having me. This is just such an amazing event. All of you are doing just ridiculous things with one of the hardest technologies that I've ever worked with. And the people making it better, people doing just absolutely amazing things with it now. None of you are boring. And this is awesome, awesome to be here. It's awesome to have this conference. I'm really, really happy to be here. So I am Jarrod Overson. I've been doing web stuff since the web was invented. Seen a lot of progress there. Been on the security side, I'm both on the attacker and defender side. I'm currently CTO working at Candle. We're building a reactive streaming framework to compose like functional WebAssembly components together. I used to work at Napster, if anyone remembers that, Riot Games, Shape Security, and I usually look like that up there, at least I used to. So before I get into the reactive streams, I want to talk a little bit about how applications evolve. And applications are like flowers. They always grow towards the sun, where the sun is asynchronous, fault-tolerant handling of distributed, arbitrary, unpredictable sized data. And I'm not sure if any of you have seen a matrix or table like this, but this is how things are described to people getting into programming now. Everyone learns about the function, the core reusable building block that you can make applications out of, but then trying to talk about futures, promises, streams, observables, whatever else becomes a little bit confusing. So you mash it up in this table to give a little bit more context, where an iterator is a function that produces multiple values, and a future or a promise is a function that will eventually give you your data. And a stream, observable, or event-based system is kind of a mashup of both, where you eventually get a bunch of data. I'm bringing this up because code naturally moves in one direction. You can turn a function into an iterator that returns one value. You can turn a function into an asynchronous function that produces a value eventually. But code resists moving the other direction. It's not very straightforward in a lot of languages to turn asynchronous streaming stuff back into just synchronous single value things. A lot of times you can't. So when I say applications grow towards the sun is eventually at least asynchronous, if not heavily streaming based. Which is tough in the WebAssembly world because we don't really have much of that at all by default unless you go through using some magic that people are making. Eventually we'll get there, and I'm very, very optimistic. Right now it's a little bit difficult. So we've been working a lot on making streams very, very rich and usable in WebAssembly because our platform is heavily aggressively based on streaming, and we've been pushing very, very far, running into hurdles, solving those hurdles for a few years now. So Wasm RS is what I'm talking about right now, and for those of you who know Wasm RS by a different name, this is a different Wasm RS, Wasm Reactive Streams. This is mashing up a lot of RSocket ideas inside a WebAssembly context, so you can essentially open up a socket into WebAssembly and treat it just like a server. And you can mash up a bunch of these WebAssembly modules together, pipe streams from one to another, and get a lot of fancy, cool stuff out of it. So the path we took to get to Wasm RS progressed over the course of many years, trying to do useful things with WebAssembly. Started off with a project called WAPC, which was originally started by Kevin Hoffman and Phil Keddy. It's a way to just kind of use WebAssembly as a component model. Now XDism is new and hot. WAPC did similar things a while ago. A cross-language way of, cross-language protocol for building WebAssembly that you can call easily in and out of with rich data, so you weren't just dealing with numbers. Then progressed to async WAPC, which is a way to do that with asynchronous calls back and forth in and out of the WebAssembly. And then async WAPC plus basic streams, which worked well until we reached the limit of what basic streams would provide us. And now we're finally at Wasm RS, which I want to give full credit to Phil Keddy for first having the idea of leveraging RSocket as the protocol and framing mechanism for getting streams into WebAssembly. We looked at a few others, and RSocket was a good combination of code that existed, good documentation, and low enough level for us to do the things that we wanted to do with WebAssembly. So that starts off with protocol methods in and outside of WebAssembly. Starts off with a host initiating your call to WebAssembly, saying, hey, make these two buffers this size. This is the maximum length that I want you to accept. WebAssembly calls back, says, all right, these are my buffers, move on. Second core protocol method is just send method. Each respective side writes frames to their buffer, calls their respective send. That's it. That's the core bit of the protocol. There is another method to map index operation names to indexes to make it a little bit faster to execute, but the core of it is just initialization and these send methods, which means that a lot of the complexity is deferred to the framing. So RSocket frames, about a dozen and a half there or something like that. These are the RSocket frames that RSocket describes for network streaming, bidirectional network streaming over TCP and whatever else you implement. We don't need all of those for WebAssembly, so these are the ones that we've implemented in Wasm RS. In both the Go and Rust implementations, we've left the network, the ones that were more important for network stuff, off to the side. So these are data structures that you build and encode into binary, write to the buffers, call your send method, and then the other side reads up until the point that that is prescribed, and decodes the frames and does whatever magic it needs to do. So the four core frames that initiate operations are the request frames. There's request response, which is a frame that initiates an asynchronous operation that takes in a single set of payload, a single set of arguments, payload, and then returns an asynchronous payload back. It's basically just an asynchronous operation. Request fire and forget takes a single set of arguments, a payload, and gives you nothing back. It's useful for like telemetry or operations that have side effects where the return value isn't important. Request stream takes a single set of arguments or a payload and returns a stream back. And request channel takes in a stream and an optional set of arguments and returns a stream back. The descriptions are a little bit esoteric. This is what it would look like in code if you were to abstract away this framing concept and provide an interface to users that they would actually want to use. Request response, which is just a simple function that returns a promise. Fire and forget, function that returns nothing. And the other two are to deal with streams. So with Rust, this is similar to what you get. In Go, we don't have as much control over the execution, so we use the observable data structures like flux, mono, observables, things like that to give you the ability to write your code in a way that handles the asynchronous nature of streams without having full control over the executor. Other frames that are important, error frame sends an error code and a message. So this can be sent as an alternate to a payload. So for every value that comes back, it can either be an error frame or a payload frame. For those of you who play with Rust or have used best practices in Go, this is similar to like your result pattern. You either get a success value or an error value, which means that these streams by default give you the tools necessary to make better decisions about what's going on. Request N is a frame that you would send back after a stream has been initiated to request an N number of frames. By default, it's coded to have a max n, so your stream is just going to be a fire hose of data down, but you can configure that to be programmatically defined, so you can tell streams to back off, hold on until you're ready for more frames, or whatever you want. Cancel frame cancels the stream gracefully, and a payload frame contains the same sort of payload data as the request initiation frames, but is used to send, it does an initiator operation. So it's used to send additional payloads in a stream, or additional fragments of a larger payload, something like that. And payload frames and the request operation frames also include the concept of metadata, which is optional by default, but these things are important to have defined in a spec, in an implementation, because at some point, things will need to be extended, and having a place where it's ready to be extended is valuable because you don't have to break anything when you need to change something. So anyone who's used WAPC, one of the things that I liked about it, and why I got started contributing back to it back in the day, was that it was very much a layered set of technologies. You could jump into it, and you could pick and choose what you wanted and make it work the way that you wanted. So we built Wasm RS in very much the same way, where you have these layers that you can pick and choose from. So at the top, you have the Wasm RS, the protocol methods, which at their core is just a way of describing chunks of data in a contract that both sides can read and write from. You could easily just take that and implement your own sort of framing mechanism or whatever you want. Then you have the RSocket frames, which you can use at their core and don't need to deal with any of the Wasm RS specific metadata or implementations. And then you have the Wasm RS metadata, which allows you to have the multiple operations within the WebAssembly module. Some other optimizations, and then below that, if you wanted to jump into Wasm RS right now, you still have spots to add your own extensibility and encoders, decoders, whatever you want. The way that you could jump in right now, we have some code generators in both like a Rust code generator build step and Apex code generators, which use message pack to broker complex data back and forth. But again, that is also pluggable. You can do whatever you want to with it. So extending Wasm RS, so Wasm RS is the unopinionated protocol implementation that allows for a lot of this stuff to work well. The way that we build things is we build things in small libraries that are encapsulated, testable, extensible, so that we don't have to apply opinions everywhere and force everyone into a lot of those opinions. Now those opinions, we pull up to where they need to go. And this is where we can show how a bunch of this functionality amounts to the stuff that you would actually want to do in an application. So WIC is a framework. We were built at Candle, which is it takes a lot of inspiration from languages like Haskell. It gives you like the functional streaming pipelines where you can string these components together and build applications out of them. We focus a lot on the statelessness, functional purity, making sure that applications don't break. Statelessness is very, very important to us, and for everyone who's ever restarted a computer to fix a problem, then you intuitively understand as well that state is one of the biggest sources of problems in software. So what we've added with the WIC extensions to Wasm RS is multiplexing. So multiplexing is the combination of multiple streams into one of these channels so that you can kind of bring in a whole bunch of streams down into one and then fan them out on either side. So this gives you the ability to take that request channel concept in RSocket that we saw before and extend that to multiple streams. And we use this in WIC to isolate or to give operations the ability to manage state within the context of execution. So rather than maintaining state within the WebAssembly module or whatever else, you get the streams in, you initiate the state that you need, and you slurp data as necessary. You deliver data out, and then when the operation is done, all state is erased and washed away. So this is a contrived example for a complex operation that might give you directions. You start off with just a single location where you want to go. Then you might get a stream of your continually updated location as you go, as well as a stream of additional stops that you might want to augment your path with. And then out of that, you get a stream of updated steps and potentially any hazards along the way. Now, with WIC and with multiplex streams, we got to the point where we needed to introduce a substream or windowed stream concept. We aggressively use streams, and when you start to make everything streams, it's easy to lose context with something like this. So if we wanted to make a process that just continually took in file names, read them, and output a stream of bytes, then that stream of bytes starts to lose context with every file beyond the first one. It's just a blob of bytes going down. So with substreams, you get this concept of this substream. So you get the stream of file names coming in, and then what you get is a stream of bytes going down. So as individual payloads expand and contract, the context of where they came from and what they're associated with is maintained throughout the application. Now, when you have the multiplexing and substreams in, then you can start to build interfaces that decompose larger data structures into the individual pieces so that you can have more granular control about how you plug everything together while still maintaining the context and relationships of those pieces of data. So an example of a component would take a stream of bytes, zip file, and outputs a stream of file names with also a stream of bytes, because a zip file can have any number of files in it. And a write component can take a stream of strings and a stream of bytes and just produce a stream of integers out for the bytes that have been written. So when you get this, then you start to be able to plug these components together and just shuffle the frames around. When you get operations outside of Wasm RS component, then you can just shuffle those frames somewhere else. All you need to do is just change essentially one byte in the frame to map an operation from one to another, and then you just shuffle the frame to the other component, and everything works magically. Now, the reason why we break things down into the smallest logical chunks of data is so that we can really plug components in wherever we want. So in this example, like if we were piping in the file name and the bytes from unzip to write, we could then carve off a pipeline for the bytes to go to a process step and then pipe those bytes back over to write without changing anything else. This is what it looks like. We're putting it into practice. I mean, this is a very, very small DSL inside YAML, but just shows how this stuff is written. You get the input, which then pipes directly to the read.file name. Read.contents goes to the unzip input, and then the unzip file name and contents go to the write file name and contents. The unzip.file name fans out to also be output alongside the bytes written. And that is just something that works nicely. That was going to be a very super exciting demo of a 1 gigabyte file being unzipped, but we're at a Wasm conference, and we're accustomed to super exciting demos like this, which is very, very fun. These are just raw packets as they're being written out, not wildly exciting, but it's the technology that is important. So before I stop here, I don't have a time, so I'm not sure exactly where I am in the schedule here. But we have been shuffling around a lot of repositories. We've extracted Wasm RS out from a project mono repo into its own organization. That means that we've lost all stars and everything else. So if there's anything that I could possibly ask you for now is to just give us a little bit of love right now and just give us our 3rd or 4th star. It would be nice. Yeah, we're putting a lot of stuff to practice right now. There's a lot of stuff that we are looking to shed as the component model matures. And as once the component model gets to the point where we can bite the bullet and go all in, then the stuff in Wasm RS shrinks to the point at which it is really only doing the stuff that is the component model can't do. So we're eagerly looking forward to full integration with component model technology as it matures. So thank you very much. And I'm not sure what our time is, so maybe questions? Comments on whether or not we are all Wasamigos? We got t-shirts made? No? All right. Thank you very much.